Florida. Thank you.
Okay, so thanks for the organizer to give me the opportunity to present our recent work. It's a joint work with Tovbis, and at the last few slides, we will talk about some ongoing project with also Jeffrey. And I will talk about the spectral theory for the Fluxes NLS and the KdV Soliton gas, right? So let's go. So here's the outline. I will briefly introduce the background theory for the finite gap theory. And then I will talk about the nonlinear dispersion relation, how we deliver the nonlinear dispersion relation from the finite gap solution theory. Then the third part is to talk about the thermodynamic limit. So we want to increase the number of gaps and shrinking the bands. Increase the number of bands and shrinking the bands simultaneously. Later, we will talk about result on computing the average conserved quantities. And in last two parts, we will talk about something called periodic gas and the ongoing project, which is the realization of KdV gas. Then I will conclude and talk about some open questions. Okay, so background. So in this background, I will take Fluxes NLS as an example. So this is Fluxes Nonlinear Schrödinger Equation. And it is a complex valued function. And xt is on the r times r plus. And there's a two typical case. The case one is when the initial data or the initial potential is vanishing at infinity. So in this case, you can apply the classic inverse scattering, and you will see the spectral data are just a discrete set of the eigenvalues to the Zaharov-Sharbut operator, right? And the case two is when the solution is quasi-periodic, or the initial data is periodic. So you will meet a periodic Zaharov-Sharbut operator. And in that part, we need to use so-called finite gap theory to construct explicit solution. And the spectral data in this case is just a finite union of bands. And so here are a couple examples of the finite gap solution to the Fluxes NLS. So the first one, you only have one band or one cut, and we call it a genus zero solution. And it turns out the solution is simply a plane wave solution. Now the second case, we have two bands or two cuts. So you will get a genus one solution, which you can write down explicitly in terms of theta function. And if you take this limit such that alpha 1 go to alpha 0, or and alpha 1 bar go to alpha 0 bar, you will recover a Soliton solution from the genus 1 solution. And the genus 2 case is you have 3 cuts. So, and also from this spectral data, you can write down the solution explicitly. And there's a limiting case when you shrink these two bands. So alpha 1 go to alpha 2, alpha 1 bar go to alpha 2 bar. You will recover so-called breadth from this limiting process. here's a picture for the genus 2 finite gap solution, and it's a modular because the solution is complex. So that's a picture of the modular of the genus 2 solution. Okay, so in general, the spectral data will be you will have two n+1 bands, and it is associated with hyperelliptic Riemann surface. So this is the structure for the Riemann surface, and I only draw the up half plane, the low half plane assumed to be Schwarz symmetry. So here are some notations for this Riemann surface, right? There's a 2n+1 branch points, which are those H for each, and there's a 2n+1 bands. So each blue one with this arrow, this orientation is our bands. Now, between the bands, there's a gap, and we denote it by Cj. And for the Riemann surface, we also need to state this canonic homology basis. So those are A cycles and B cycles. And with this kind of Riemann surface, we can define two very important meromorphic differential called quasimomentum and quasienergy. So this part of a theory is from Forrest Lee's paper, and the definition is the following. So dp dq are meromorphic differential with pole over orders 2 and 3, and you can see actually here. So the second one is the expansion at infinity. You will see this one. This differential dp has a pole over order 2, which come from this dz, and there's no other singularity, right? And this one has order 3 at infinity, and it is normalized to be 1 and 4 here. So this asymptotic is only on the main sheet. On the second sheet, because this Riemann surfaces have elliptic, on the other sheet, you have to flip the sign. And the third requirement is we require this quasimomentum, the periods for the quasimomentum and the quasienergy to be real. So with those requirements, dp dq are uniquely defined. Now, what can we do with those dp dq? Well, again, from the Forrest Lee's paper, we define the wave numbers and the frequency by the following relation. So Kj is wave number. It is just the A cycles of the quasi-momentum, and frequency is the A cycle with the quasi-energy. Well, here, those blue ones are the B cycles, and we will talk about this in few slides later. And those are called the carrier wave number and the frequency, and the red one are called the Solitonic. And as we can see from the requirement for the quasi-momentum and the quasi-energy, we require all the periods to be real. So apparently those wave numbers and frequencies are all real. So with those things, we can now talk about the non-dispersion relation. And here, you apply the Riemann bilinear relation to the Riemann surface with the help of the normalized holomorphic differential, as represented by this formula here. you can see you will get a large system, linear algebra system. And this system is called the full version of the non dispersion relation. So you will see both the carrier wave number and the Solitonic wave number. So okay, so that's the full version of the non-dispersion relation. Now, if you take the imaginary part, so in this full version, you take the imaginary part, you will get rid of this carrier wave because this guy is real. So you will get the following formula. Here, I just write the normalize the holomorphic differential explicitly, and the right-hand side comes from the residues computation. So this is the this part without this red one is the normalized holomorphic differential, and you times z, you got the right-hand side for the first equation. And if you multiply by z square, you will got the second equation for the frequency. And those equations are our main object in the current talk. And well, here we consider the imaginary part. Of course, we can take the real part. And if you take the real part, you will see the following system. And this system, first of all, this system, you have the same number of unknowns and equations. And also from the periods of the Riemann surface, you will see the positive definite. So those coefficient matrix is invertible, and it guarantees the existence of the system. So you have a unique solution for K and omega. And so if you solve the imaginary part, so those K and omega are already known. So this equation, it's not actual equation, it directly comes from the previous solution. You can define the carrier wave number and the carrier frequencies by these relations. All right, so next, let's so far we simply discussed the finite gap solution to the fNLS, and we talk about the spectral data for genus 2n solution, and we define the quasi-momentum and quasi-energy. So here, dPn, dQn, this index n is to emphasize the geometry of the Riemann surface, the genus of the Riemann surface is 2n, right? And we also define those wave numbers and frequencies. Now, using the Riemann bilinear relation and the normalized holomorphic differential, we state the non-dispersion relation. Now, next, we will talk about several questions. We will discuss the thermodynamic limit. So in the previous slides, we only consider the finite gap theory. So everything is finite. Now we want to take the limit as n go to infinity, and simultaneously we will scaling those bands. And this part will lead to the integral equation version of the non-dispersion relation. Now, after that, we can define so-called density of states. And using the density of states, we can computing the average conserved quantities. Then after that, we will talk about periodic gas motivated from WKB analysis. And in the last, we will talk about the one ongoing project for the realization of Lamé gas. All right, let's go. So thermodynamic limit of the non-dispersion relation, right? So here, for we first need to define what is the meaning of a thermodynamic limit. So for each band, we define the center of the bands as Cj, which is the average of these two branch points, and the bandwidth is defined as the, so this is half of the bandwidth using delta J, right? And so in the thermodynamic limit, we will introduce a density function phi z, which is defined as the following. So this, which controls how the center of the bands are distributed. So n is to scale the to scale the center. So the bands will shrinking in some compact region. Now, the second point is to describe how fast you shrink the bands, right? So that is characteristic characterized by this function nu. So nu is a function describe how fast you shrink the bands. So in this case, if delta shrink like exponential like exponential, so this case is called the dense gas limit. Now, if the band shrink slower than the exponential, you will get so-called condensate limit. And if it is really fast, so really fast means nu is very large, and you will get so-called ideal gas. So those are the concepts in the thermodynamic limit. Now, what can we do with the thermodynamic limit, right? Also, we need to define some concepts. So in the thermodynamic limit, in that Riemann surface, if you shrink all the bands, so remember there's a 2n+1 bands, and there's one exceptional band called gamma zero. But in the Soliton gas limit, we will shrink all bands, include the exceptional bands, and n will go to infinity. So this is the Soliton gas limit, and the Brazil gas limit is the same, but you will freeze one. You will freeze the exceptional bands gamma zero, and all other bands are taking the thermodynamic limit. Now, of course, there's since you can freeze one band, you can also freeze a finite number of bands. So that is so-called elliptic gas limit. So you freeze finite number of bands and shrink the rest of the bands in the thermodynamic limit things, right? So here is a lemma about the coefficient for the nonlinear dispersion relation system. So remember, this system, we need to compute the B period of the normalized differential. Now, what is this guy behavior in the thermodynamic limit? It's given by this following lemma. So due to the Schwartz symmetry, we can always combine the pair, the conjugate pair. So let be tilted as you have bk and b minus k. So bk and b minus k are the b cycles. Bk is the one in the upper half plane, and b minus k is the conjugate of this. So we will consider the Brazil gas limit here for this object. So gamma zero is freezed. And in this lemma, you will see this B periods can be computed approximately like this. So this formula is looks very complicated. and you will see this red formula here, which is very complicated, but this part is very simple. So we will talk about the reduction of this case when you taking the Soliton gas limit. So in the Soliton gas limit, which means delta zero will go to also go to zero, then you will see this completed term will disappear. You only got this log kernel, this log term, and we also delivered so the first formula is for the off-diagonal terms, and in the diagonal term you will see this is 2 log delta j over I pi, and delta j controls how fast delta j is the bandwidth, and it's controlled by the how fast you shrink the function nu, right? So and also we give the arrow estimate for those formulas. And here R0 is square root of z square minus delta 0 square. So delta 0 is from the edge of the exceptional band gamma 0. And okay, so we have this lemma, and based on lemma, we can now take the limit to this. So back then we have a large system with algebra equation, and now we let the size of the algebra equation go to infinity, and you will see those summation will become Riemann sum when after properly rescaled. So that's the that lead to the following integral equation. So this equation is for the Soliton gas limit, right? So in this case, delta 0 will go to 0 also, and you will see this red one is disappear, only this log term remain. So this log term will become the kernel for this integral equation, and sigma comes from the diagonal term, which is determined by how fast you shrink the bands. And the right-hand side is from the residues computation, just copy. So, so what is this U? So U is U hat times phi, V is V hat times phi, sigma is this nu, which the exponential component in the bandwidth, or the log of the bandwidth, and divided by phi. So here we had the interpolations of kj over n and wj over n. Those are the wave numbers, right? So also this integral term describe this interaction of this large system. So you can imagine the gas as a large system of a lot of particles. So this kernel describe how those particles interaction with each other in the larger scale. So in the finite particle case, you will see this actually is the phase shifter of the interaction of solitons. And that is a natural generalization to the gas situation. You will get the integral with this kind of kernel. So here, this equation is a Fudong integral equation in general of third kind because sigma z will have zeros. Now, by the way, this function u has a name. It's called the density of states. So the solution to the first NDR equation is called density of states. And this v is the temporal analog. And this integral equation is studied in recent work by Kura and Tovbis. They under some mild restriction on the support of this DOS, and on the sigma, you will state the you will establish the uniqueness and existence of the solution to both equation, and also you can show, which is very important, that this DOS is non-negative. So this non-negative because it has a physical meaning. It's just the density function. So now let's talk about two other cases. So here we consider the Soliton gas limit and the dense limit, right? Now, we can also consider the condensate limit or and the ideal gas limit. So what are those cases? This essentially means this band shrink really fast. So it's faster than this this exponential turn. And so if it shrinks really fast, wait, let me see. So you will see. So first this is a condensate case. So when you shrink the bands really slow, and in that case, the sigma in this equation will dominated by the integral term. So eventually, sigma will go to 0. So the equation for the condensate will be just this equation without sigma u. And in that case, we can explicitly solve those NDR equations by applying some formula from finite using finite Hilbert transform. And those equations are called the Fredholm equation of first kind. Now, in the ideal gas limit, when you shrink really fast, right? So delta is very slow than this exponential turn. So you shrink very fast. In that case, this this integral term is dominated by sigma. So eventually, you will see the equation is just the sigma u equals the right-hand side. And that case is pretty trivial. All right. Now, what about the brother gas, right? So in the brother gas, you will see this big red chunk of this from the lemma. Well, it involves this R0 and R terms. It's very complicated. And in this situation, the existence and uniqueness is still open. And also, in the brother gas case, the positiveness of U also. So that's the NDR for the brother gas limit. All right. Now, we can also combine both. So we will get the full version of the NDR equation. So in this case, you will see the both the both U and U tilde. So what is this U tilde? The U tilde is from the by interpreting those carrier wave number. So U tilde interpret the KJ tilde, which is the carrier wave number. So, and the U tilde Z will be called carrier density of states, right? And later on, we will discuss how to connect those U and U tilde with the quasi-momentum differential in the thermodynamic limit case. So now with those nonlinear dispersion relation and DOS properly defined, we can now talk about the average density. So again, following from Forrest Lee's result, the average density comes from the expansion of this quasi-momentum by expanding this quasi-momentum differential at infinity. So you will see the following expansion, and this IMN is the average density for the genus N solution. So IMN is the average density, right? And there's two cases will be established. And the first case is when N is very, very large, but still finite. And in this one, we still under the framework of finite gap solution. Now, the second case is we let N go to infinity. And that is the gaseous situation. Now, so in the for the Soliton gas case, we can take the we get the following result. So we compute those IMN explicitly in the following formula, and it's very clear. And this is just the B cycle of this polynomial. And that is wave numbers, and you sum them up. And we also give the arrow for large N, right? And in the limit, in the Soliton gas limit, you just remove those arrow turn, and those wave numbers become the density of states. So you get this clean formula for the average density for Soliton gas. So U is the density of states, and here is the imaginary part of some polynomial. So this, so here this lambda is some reference measure. If the gamma is just some arcs, it will be the arc length measure, and if gamma is 2D compact, it will be area measure. So this is the formula for the Soliton gas. And well, for the Brazil gas, which is more general, you will see a very complicated formula. And the thing is complicated is because this term comes out, and this R0 again is this square this radical because the freeze the band, and we have this formula. Now in the limited case, we need to assume that this measure converge to the, so this interpretation of those wave numbers weakly converge to UZ, the density of states. And we can state the result for the Brazil gas, the average density for the Brazil gas. which is the foreign formula, which is also pretty clean here. The only the difference is this imaginary part. So this imaginary part Fm is this term. So that is the antiderivative of this this guy, and this square bracket plus means the regular part when you expand this thing at infinity. So you have this radical. When you expand that, you will get a series, and it takes the regular part. All right, so that is the Brazil gas. Now, here is a sketch of the proof, and I will just mention two things. So one thing is about this RZ. RZ is our Riemann surface, is the radical. So you will see in the limit, this radical RZ for the genus 2n Riemann surface can be approximated by the following formula. So, and there's some arrow estimate on that, which is very fundamental to give those arrow estimate in our formulas here, and for the Soliton gas distance. So that is one point. The second point is this this G function stuff, but so and we will see this in a moment soon. But this technique is from the Riemann-Hilbert formulation of this finite gap theory, but since I totally skipped that, so let's just move on to the next slide. So the next one is we want to connect this density of states and the limiting quasi-momentum differential. So dp without index is the limiting quasi-momentum differential. So here is the definition. Before we defined the dpn as a series expansion with coefficient im, comma n. Now we just remove this capital N in the limit, since we already compute those im, and this series will define this in certain in the region of convergence, will define an analytic function p, right? And also you can write this as the derivative of another analytic function, and that is actually the G function here. But so this Gm is defined as those formulas, which comes from the result of im is simply multiple by m to im, you will get Gm. So now the 2gx, this G function is defined as the antiderivative of this this guy, this series Gm over Zm. And this G, as I mentioned, is from the Riemann-Hilbert formalism of the finite gap theory. Okay, so now with this definition, we computed the relation between the DOS and the quasi-momentum differential. So they are associated by a Cauchy transform to the density function. So what is this U hat? So this U hat is a function such that this is true. So U times arc length measure is U hat times d mu. So this U is just take care of the geometry of this contour gamma. And this C gamma is the Cauchy transform. Now, from this formula, and this formula is true when Z is off the contour. Well, if you take the boundary value, you will recover those you had and the average of the dPdZ, which those formulas immediately comes from the primary formula from this relation here. Okay, so now let's go back to the full version of the Nonlinear dispersion relation. So here is the full version of the Nonlinear dispersion relation, and in the most general form, with Elliptic gas limit. So you have this complicated term. Now you will see this U-tutor, which is the carrier density of states, right? Now, using the G function, we defined as antiderivative the quasi-momentum differential. We will recover, we will establish the following relation. So sigma U is the imaginary part of Z minus 2gx, and the carrier density of states is the real part of the boundary values. And so that is the connection of the G function and the carrier density of states. Now, next topic will be the periodic gas. So what is a periodic gas? The result is mainly motivated by a recent paper by Biandini Andre in 2020. They're using a formal WKB to get some beautiful formula for the Fourier discriminant of the periodic Zaharov-Schubert operator, which corresponds to the Foxing nonlinear spectral problem. And from there, we one can compute the density function phi and the function the scaled log bandwidth nu. So those functions are computed explicitly in terms of following formulas. And so the here Q is the potential, which is a 2L periodic potential, and in its period, it's just a one hump. So it go up on the first half and go down on the second half period. So with phi and nu defined, we can obviously compute sigma, which is 2 nu over phi. And so that we got all the information, all the coefficient for the nonlinear dispersion relation, the integral equation version. Now, what result can we have? So in the periodic potential case, we can actually solve those nonlinear dispersion relation integral equation, and this is the solution. So the solution to the first nonlinear dispersion relation is given by this, and you will see if you check the formula, compare the formula with phi, you will see this is proportional to phi. So you will see this is the numerator is exactly this numerator here, and this is a constant. Also, this is a constant. So this density of states is proportional to the density function. So this density function controls the center of the bands. And also, we can apply of a result on the average density of the gas. So with directly plug into the formula, we can use this U and we can compute explicitly this average density for the periodic gas is given by the following formula. So it is just some constant times the integral of the moments of this potential. Okay, so that's a short introduction for the periodic gas. Now let's talk about some ongoing project with Alex and Jeff. And so in this part, we consider this Lamé potential. So in the elliptic form. So this Qx is a potential for this operator here, the Schrödinger operator here, and it is given by minus g plus 1. And this p is the Weierstrass p function. And shifted by a period. So this so Weierstrass function is double period, and you shift by the pure imaginary period, you will make this function a real function. So it's the half period, sorry, and so this G will with this kind of potential, you will see the spectral data will be G bands, not including the infinite long bands. So we will denote a small parameter epsilon square as the receptacle of this 1 over g plus 1. Now, to create the gas, we need to let this the number of bands go to infinity. So G will go to infinity. So this epsilon will be very small. And then the spectral problem for the Schrödinger operator L looks like the following form. So F is eigenvalues, F is eigenfunctions with eigenvalue eta square. And the the potential is the Weierstrass p function with shift. So we apply a result by Weston-Keller. We can compute a asymptotic formula for the Fourier discriminant. So this delta represent for the Fourier discriminant, and it has two parts: exponential part, which can control how this discriminant grows, and this cosine part control how this discriminant oscillating. And this S1 and S2 is given by the following formula. So here, positive means we're taking the maximum of the, so basically it's taking the positive part of the underlying function. So you will see, so this is the formula for S1 and S2, and it's related to the potential, the Lamé potential with just p function here, right? Now we have a quick observation. So the distribution of the center of the band will proportional to the derivative of this S2, which controls the oscillating. So with this observation, you can see, you can compute this phi as following. So that is from the derivative of Sn, and this constant is the normalized normalization constant, so that the total mass of this density function is just 1. And also V will be defined as pi over j times S1. So this formula gives a representation for nu. So when you have phi and nu, you will you are able to compute sigma. So you will get the coefficient for the nonlinear dispersion integral equation. Here, the constant J is given by the zeta function. Okay, now let me talk about how to solve the nonlinear dispersion relation for the KdV case, right? So in the KdV case, we have the following two nonlinear dispersion relation. The first one, the only difference is just the right-hand side. So the first one is eta, and the second one is 4 eta cubic, which comes from the dispersion relation for the KdV equation. So and sigma comes from the formula 2 nu over phi, and for the periodic gas, we can compute sigma explicitly. However, sigma is very complicated, as you can see from those formulas, right? So that rests two difficulties. The first difficulty is sigma may have 0. Although sigma is non-negative, but if sigma has 0, it will cause a problem to the equation. So the integral equation will be so-called third kind, and in general, it's very hard to solve. And here also for the Lamé potential, so if you do the ratio of nu and phi, you will see the behavior near 0 from right looks like this, and that is so that means it has a 0 at 0, and that is not good. And the second difficulty is to prove the positiveness of the first NDR, because U is the density of states, and physically it should be positive. And so in general, it's very hard to prove for Fredholm integral equation of third kind, and to prove the positiveness of this solution. And for the existing uniqueness for the first NDR equation for both equations, and using which you can transfer to Hilbert boundary value problem. So equation 11 is first NDR. When you extend this U orderly to the, so here is just the right half 0 to m. When you extend to the left half minus m to 0 orderly, you will get the green kernel, this log term here, which is called green kernel, will become a log kernel. So you will get this similarly simple integral equation. Now, if you define capital F as follows, so it's minus I times eta minus I of the integral with this log result with bracket here, and U is the DOS. Then you do a quick computation to the boundary value, you will see the real part of the derivative, or derivative of the real part of F is pi times U, and the imaginary part, the boundary value of imaginary part of a capital F is minus sigma times U. So the imaginary part is, you will say it is simply this, you will change this bracket to modular, so you can apply this integral equation to get rid of this log, and you will get this sigma, and because this eta will cancel this eta. So you got these two conditions on the boundary, and apparently f is analytic function away from the cuts. So here we will take the principal branch for the logarithm. So away from the branch cut, you will see this is an analytic function. So those three together, you will it's actually a Hilbert boundary problem, but involve derivatives, which is called generalized Hilbert boundary problem. So here is a way to solve this equation. So we will introduce a little f as the radical of this thing. So Q is the potential and minus eta square, and this also will give you a multi-value analytic function. And you will see the sigma is simply can be represented as the ratio of the imaginary part of little f and the real part of the derivative of f, right? So, and from the relation, you can remove this u by taking the ratio of this two relation, and you will recover this kind of single relation here. So the imaginary part f times the real part of f prime plus equals imaginary part of f plus times real part of f prime. Also, we have from the definition of a capital F, we have this behavior at infinity when eta go to infinity. So when eta go to infinity, since this u is odd function, so in general we have this kind of behavior, but since u is odd, so this guy will disappear. So that will be the boundary behavior at infinity. Now, a quick observation you will see from you can easily see from this equation 15 that capital F is proportional to little f will be a solution. And you check the boundary, you check the normalization condition 16, you will see you can determine C. And now from this boundary value behavior, we can recover this DOAs simply by taking the real part and take the derivative. So that will give you the solution to the first NDR. So whether this solution is unique or not, we probably still need to go back to the potential theory method. And here, one open question is, when the right-hand side is not eta, but eta cubic, so you will change the normalization condition to eta cubic, can you still find the solution? And that is the open problem. And so at the last minute, I will show so since we cannot find the solution to the second NDR equation, and we try to numerically solve it. So here's some results for the numeric solution. The first picture shows the solution to the first NDR. So this red one is the analytic solution because we can solve it explicitly. And the black one is the approximation when you take genus to be 1,000. So you will see it is pretty close. And here is the solution for the second NDR by solving the large system, right? And you will see there's a small portion which is negative, and that in the corresponding to the Soliton gas means part of this gas will move left and part of the gas will move right, because the speed and the direction will determined by the ratio of the V and U. So negative go left, positive go right, and it will be good to establish those results analytically for the second idea. So, and the conclusion is basically I just introduced the finite gap theory for the Fluxing analysis, and then talk about thermodynamic limit, and then introduce periodic gas, and last we talk about ongoing project for the Lamé gas. Now there's two open questions. The first one is to solve the second NDI equation with non-negative sigma, and who has finite number zeros. And the second one is to prove the uniqueness and existence for the Brazil gas case. And that's all for my talk. Thanks for your attention.
Thank you, Fudong. Let's thank him. Any questions? Maybe I have a small question here. For the Lamé potential, so the solution, the initial condition you show, you're saying that potential is high genus, but is still one phase solution. Is that my understanding? Is that correct?
It's still multiple phase.
Right. But still, you know, so the G is the genus here, right?
The G is genus.
But it's still one phase solution because of the pay function. It's a very degenerate one.
Yes, it's very degenerate.
Times
so
zero. Okay. Yep.
Yeah, it's accumulated at one
Okay.
base basically.
Thank you. Any question? All right, let's thank Fudong again. Thank you. And all right, so our